Hello everyone. In last lecture I have already started about fundamental of different types of welding heat sources. There I have already discussed in details about Goldach double ellipsoidal heat source model. Its details derivation I have already discussed in last lecture. Today I will also discuss about some other very important heat sources which are widely used in the field of welding. That related things in details in today's lecture I will discuss. So, today first of all I will discuss about how the means Goldach double ellipsoidal heat source parameters we can decide or calibrated by experimental observation. First of all I will discuss about that. Then I will discuss about some other heat source model like semi ellipsoidal heat source model. I will discuss about Gaussian distribution of heat source model. This is actually a two dimensional types of heat source model. Then I will also discuss about Avogadro-Schaff heat source model. Apart from these things I also discuss about some other heat source model which are mainly used for high energy density welding process like laser beam, electron beam, even plasma arc welding process also where we can use that types of heat source model. So, first of all I will discuss about experimental parameters calibration for Goldach double ellipsoidal heat source model. So, in last lecture I have already discussed what is Goldach double ellipsoidal heat source model. So, in front part of the heat source model we got the volumetric heat distribution in watt per meter cube you can say, and this is for front part of the double ellipsoid, and this is for rear part of the double ellipsoid. This is generally for moving coordinate heat source. Here we consider zeta is the moving coordinate, and once we consider about fixed coordinate heat source, this equation become like this. Then zeta generally convert to z for double ellipsoidal heat source model, that is the fixed coordinate system z, and what v is the welding velocity, tau is lag factor, and t is the time. I have already discussed in details about these things. From this equation what we got to simulate this heat source model, we need some parameters. What are those parameters? Those parameters are you can say A, B, CF, CR, then you can say another some experimental parameter also required, that is eta efficiency, voltage, then you can say current, and apart from these things we need to know also how to calculate Q value. So, Q value is equal to net heat input, Q is equal to eta into Vi, its unit is watt. Now, how to calculate this semi axis of this double ellipsoid, and how to calculate what is this net heat input, this you have already got the idea. This in detail experimental how we can calibrate this A, B, CF and CR, that related things I will discuss now one by one. So, apart from these things you know there are another two parameters we use. One is called F, you can say front part, and fraction of heat you can say in front part and fraction of heat in rear part. This also I have already discussed how to find out these things. So, Fr generally you can say 2 Cr divided by Cr plus Cf, and Ff generally we know this 2 into Cf divided by Cr plus Cf. So, this in details I have already discussed. So, today first of all I will discuss about these parameters, how to calculate experimentally, this I will discuss first. So, you see there are generally various way we can decide this heat source parameter, but from experimental observation generally we can calibrate this parameter by considering the fusion zone of the heat source. For this generally here one techniques we use for calibrating this heat source parameters by considering well bed end crater and well bed cross section. These two generally geometry consider for calculating of you can say A, B, CF and CR. How everything in details I will discuss. So, for calculation of you can say A and you can say CF, CR, we generally consider N crater. N crater, what is the definition of N crater? Generally it is created, let this is a weld line or welding is done. At the end of the welding process, there you can see create a impression, you can see this is a impression which is generally called N crater, because it is created after completion of welding process or at the end of welding process, that is why it is called you can say N crater. So, in this N crater it is a cavity, you can say it look like a cavity which is developed at the end of weld due to what? Due to shrinkage of weld metal during solidification. Generally what happens when this molten weld pool solidify, at that times generally here there is create a cavity like shape which is looks like this. So, its shape is looks like double elliptical types of shape you can see. So, one of the part is you can consider as for front quarter ellipsoid and another one is back quarter ellipsoid you can see. So, how to calculate in next slide I will discuss. So, from here itself you can calculate the directly you can measure this CF front part and this is the CR rear part of this 2 parameter of this double ellipsoidal heat source model. And apart from these things, here also we can calculate the semi axis of A also we can calculate, this is the A. How to calculate this thing? This I am just showing. So, for this generally what we need to do, first of all we need to do a welding. This is a actual welding we performed. From this actual welding you can see this is the weld bead, and if we draw the weld cross section, if we draw the weld cross section, how it's look like, you will see the weld bead cross section look like this. This is the weld bead cross section you can say, that means there is a some top surface or you can say top bead height, as well as at bottom side also there is some bottom bead height is also there. So, this top side whatever the portion is above the you can say plate surface, that is generally called top bead height, or it is also called top reinforcement. On the back side whatever the portion generally out of the plate surface, that is generally called bottom reinforcement. Little bit here I am writing bottom reinforcement. So, after welding we have to first calculate this, what is A, this A I have already shown you. So, I have to first define this what is called N crater dimension. You see this is the N crater dimension I have decided, okay. And from here I need to measure you see this A value, and this is the CF value, and this is CR value. This you can easily measure by using the scale, or you see the right side I have already shown the scale. So, from here itself you can easily measure this one parameter along you can say x axis, another 2 parameter along z axis is CF and CR, or welding direction CF and CR you can easily calculate. Then for measuring this B value, that means parameter, this B parameter generally along the depth direction, I have already for double ellipsoid I have already told you, it is at the depth direction means let this is the double ellipsoid, okay. So, at this location you see, at this location whatever the depth you get, this is generally considered as B. So, this B how we can calculate? For this generally what we need to do? We need to take the cross section of this well bit geometry. Cross section of this well bit geometry, that means perpendicular to the well line we need to cut a section. This is a well bit, just I am showing here, then it will be more clear to you how to cut this section. Let us consider this is a well bit. Okay. So, what are the things we need to do? We need to cut a section perpendicular to the well direction, perpendicular to the well direction. This cross section generally here it is showing. This is the actual experimental cross section. From here, how to measure the B? We need to measure the B by taking the distance from top surface of the plate. You see, always you should keep this thing in mind, because we generally used to apply the double ellipsoidal heat source along the surface of the plate. What I am telling understand, that is why you see we need to take the distance from top of the, you can say top of the surface of the well bit to you can see bottom till depth of the bottom reinforcement, out of the overall bottom reinforcement is taken place. So, bottom peak height you can say we need to consider, this is generally considered as B value. So, how to get this cross sectional view? For this generally we need to use some etching operation. For etching operation of steel plate generally we use nitrile solution, 2% nitrile solution. Here I have already written. What is 2% nitrile solution? 2% nitrile solution means in this solution there is 2% you can say HNO3 nitric acid, and there is 98% methanol, that is CH3 OH, this is generally methanol. So, that is why it is generally called nitrile. Nitrile means from methanol all is coming and nitric acid NIT is coming, what I am telling understand. So, this makes a 100%, if it is 100 ml of what is called nitrile solution, then there will be 2 ml you can say HNO3 and 98 ml you can say what it is called methanol. So, total 100 ml nitrile solution will be you can say make by using this method. This nitrile solution generally we use to see this cross section, this you should keep it in mind. Then only we can see the you can say fusion zone boundary, you can see this is the fusion zone boundary and bit geometry, top reinforcement, bottom reinforcement. Even we can if we etch it, if we means polish this surface further, and if we further etch it and if we magnify this section, then we can also measure the heat affected zone size and all, and even microstructural grain size also we can measure by using optical microscope. Then some other high resolution microscope is also there, that is generally same. Then TEM, by which we can measure further very teeny or a small you can say crystal characteristics also we can see. Okay. So, generally by using this nitrile solution and taking the cross section we can measure this B value. So, this is the way generally to measure different parameters of this Goldach double ellipsoidal heat source model, this you should keep it in mind. And how other Q value is required to calibrate, that we can calibrate from the heat source itself, in the sense generally whatever the power source we use, that power source generally will have a efficiency. So, by this we can measure this, we can consider this eta value, and from this power source itself we can easily measure what is welding voltage and what is welding current. Okay. So, these are the parameters required generally in case of what it is called double ellipsoidal heat source model. Okay. Now, we will discuss about semi ellipsoidal model. So, before this we have already discussed about double ellipsoidal model, where do we consider two ellipsoid. You can see two ellipsoid means what, one is front part and another one is you can see another one is rear part, like this double ellipsoid. But in semi ellipsoid we will consider only on top surface ellipse. Okay. on top surface ellipse, and there is generally depth, there is a depth as it is a 3 dimensional types of shape. So, you can say this is a half of a ellipsoid, that is why it is called semi ellipsoidal model. Okay. So, in semi ellipsoidal model, here one things you should keep it in mind, here generally you can see CR and CF, here generally CR is equal to CF is equal to you can say C, this you can consider here, what I am telling, understand. So, here generally distance of this front portion, let us consider this is CR or CF, let us consider this is the welding direction, here we consider the different axis system, here generally we consider this x is the let us welding direction, but in this case as here we consider the welding direction as x, here in this model we consider let us welding direction is x, that is why here instead of CR CF here we can consider AR is equal to AF is equal to you can say A, this you can consider. In this model you can see here welding direction we consider as let us x direction. We can consider z direction, x direction, y direction, whatever it is, but in this model as we consider here x direction. So, here generally you can see your moving coordinate system, let us if the moving coordinate systems is x dashed, this will be related to fixed coordinate system x plus you can see v into tau minus t, this you should keep it in mind. If the heat source is started beyond the fixed coordinate heat source, let us consider you see, let this is your welding direction x, this is your y and thickness direction is this, and your heat source is let us consider your heat source is started from here, and here fixed this is your z, and this moving coordinate heat source, let this has a x dashed and it y will be same and its z also will be same, which is parallel, only this moving coordinate system x will be different. Then how it is related, this I have already discussed in detail in previous lecture. Here one things you should keep it in mind, here you see q is equal to whatever the q here it is showing, this q is equal to generally net heat input which is eta Vi, and as here you can say CR and CF both are same, that means AR and AF both are same, that is why here we need not to consider front portion and back portion, that fraction of heat deposition. So, here that is why here only one equation you can use, only this one equation we can use here to consider this heat source model. This you should keep it in mind, because here we have not considered that rear portion of volumetric heat source and front portion of volumetric heat source. Here we consider full volumetric heat source which is a semi ellipsoid, this you can see from this figure itself, this you should keep it in mind. Now, how this volumetric heat source equation we derive, the same things we discuss in details in Goldach double ellipsoidal heat source model, or but the way I discussed there, that means first of all you need to find out this QM in terms of this A, B, C parameter, how I have already discussed, what is the value of A for calculating these things generally in details I have discussed in double ellipsoidal heat source model, this A, B, C value. So, based on these things once we derive these things, and this is the semi axis dimension of this ellipsoid along x, y and z, along x direction is A, along y direction is B is, and along z direction is C. So, this way generally you can easily find out what is the volumetric heat source model vol for semi ellipsoidal types of model. Okay. Here generally one things you should keep it in mind, these types of heat source model we generally used in the case of high power density beam. Apart from this semi ellipsoidal model, some other models also are there, which also we generally used in case of what it is called high power density welding process, like laser beam welding process, electron beam welding process. like there also we use some cylindrical types of heat source model, conical types of heat source model, that related things also I will discuss in subsequent slide in details. Now, we got about double ellipsoidal heat source model, about semi ellipsoidal heat source model. Now, I am going to discuss about what? Now, I am going to discuss about what it is called Gaussian distribution of heat source model. This Gaussian distribution of heat source model is generally the two dimensional heat source model. This heat source equation can be written as Q r, which is equal to generally 3 q by pi r square, 3 r square divided by this capital R square. What is R square? Small r square is equal to, you can say, x square plus y square, and this R square is as a name, that is generally called characteristics radial dimension distribution parameter. It has generally defines the region in which 95% of heat flux is deposited. This you should keep it in mind. This capital R, how it is defined? It is defined in such a way where you can say maximum, let us consider this is a heat source model which is circular, let us consider is in nature. It can be circular or it can be little bit teardrop types of shape, also it can have, because this A and B value, if let this is your A and this is your B, if A is equal to B is equal to same, that means R, then it will be a circular types of heat source. If A and B will be different, then it can be a elliptical types of also heat source. Okay. Now, that also I will discuss in details here. So, in this generally if the heat is distributed this is the plate surface where heat is distributed in Gaussian in nature, that means where maximum heat is at its center, this is let us q m. So, in this as it is a you can see as it is a two dimensional heat source, that means here the we are considering heat is distributed over the surface of the plate only. Here this what is called through thickness dimension heat source we are not considering. So, these types of heat source model popularly used in case of, you can see in case of thin types of thin plate, as well as it is also popularly used in case of TIG welding process, or you can say this has a name GTAW also, gas tungsten arc welding process. This types of heat source model is popularly used, where you can see no consumable you can say electrode is used. In TIG welding, you know, there is used a non consumable tungsten electrode, which is not consuming during, that means which is not melting during welding process, where generally from this electrode there, let us consider this is the TIG electrode, from here generally you see there is developed a arc, this electrode is non consumable. So, for that generally this arc which is developing, this arc generally distributing over a circular area, or it can once it is moved generally it is distributed over a, you can see, elliptical types of area. This heat is two dimensional heat source, if will move over the thin sheet plate, then whatever the temperature distribution, then what happen contour of the weld pool or molten pool generally we used to get, that generally quite well matched with experimental result. That is why here instead of for thin sheet or this stick types of welding process where non consumable types of electrode is used, they are generally these two dimensional types of Gaussian distribution arc is popularly used. This you should keep it in mind. Then how this heat source model is coming, that derivation little bit I am going to discuss. So, like in previous case I have already discussed in Gaussian distribution of heat source model, the same way here in case of two dimensional case, the heat flux distribution along x and y direction can be represented as a q max into e to the power minus a x square into e to the power minus b y square. This way I can represent, correct. So, its unit will be, always you should keep it in mind, this is a heat flux, that means heat per unit area, 2 dimensional case, watt per meter square, this you should keep it in mind. What is Q m? Q m is the, here I am writing, Q m is the maximum heat flux, you can say maximum heat flux. But in previous Goldach heat source model I have told you that is maximum power density, that unit is watt per meter cube, but here as it is a 2 dimensional case, its unit is watt per meter square, and you can see here generally 2 exponential terms we have considered, that is generally x and y. So, here generally maximum heat flux Q m is equal to maximum heat flux, and here how the heat source model is going, that I am just showing. Let us see, here the heat source is started from here. Let us consider this is our x coordinate and let this is our y coordinate. So, let us consider this is our x, and this after some time this moving coordinate heat source has a coordinate system which is moving coordinate is let us x. So, that is why here I am representing x dot and this is your y. So, fixed coordinate is, let us consider, has a origin O, and moving coordinate has a origin, let us consider this is after some time it is become O double dot. Initially this moving coordinate heat source has a center, let us O dot. So, from here to here let us it takes a time tau, and total time from here to here let us it takes a time t. So, in last lecture itself I have already discussed about what is the relationship between moving coordinate axis with fixed coordinate axis. So, fixed coordinate, here I am writing fixed coordinate is x y coordinate system, which is actually I am writing here fixed coordinate system, and x dot y is our moving coordinate heat source, moving coordinate heat source. Then we know what is the relationship between x dot and x. So, x dot is equal to, you can say, x plus, if the welding speed is v, tau minus t, correct. This I have already discussed, where v is equal to welding speed. How it is coming, everything in details I have already discussed, welding speed. So, I am not going in details further. Now, from this equation, how this that means q x y is coming as you can say 3 q divided by pi r square exponential to the power minus 3 x square by a square, or you can say r square if you consider, plus y square by r square. How it is coming, everything in details I will discuss. Or you can see this also you can write as 3 q, if this r is different then you can write pi by, you can write as pi by a b exponential to the power minus 3 into x square by a square plus y square by b square, if this a and b is different. If a and b is same, if it is circular heat source then a and b equal to same, if it is elliptical types of heat source then a and b will be different. Then how this equation is coming, this I am going to discuss little bit, okay, because this already you know. Now, from the Gaussian distribution, let us consider this is your a along x direction and this is your b, and here generally let us consider this Gaussian distribution is distributed, Gaussian heat is distributed, which you can write like this. So, this I am writing drawing like this. Okay. So, let us consider here my heat flux, our heat flux intensity is maximum, this is the maximum heat flux intensity, and this A and B is defined is that location. Here you can consider this A and B location, you can consider as those location where you can say 5% of heat flux density is there, or you can say 5% of heat flux is distributed at that location, here as well as here 5% of heat flux is distributed of this maximum value, this you should keep it in mind. So, based on this actually I will just now derive this what it is called equation. So, in last lecture itself I have already discussed, that means whatever the heat is coming on the arc, in this arc how much heat is coming, this heat generally you can, this net heat which is coming from the welding power source and which is distributed to this heat source, this net heat input you can write as Q is equal to eta into V into I, correct, this net heat input. This is generally distributed in Gaussian manner in this what it is called surface. So, if it is distributed in Gaussian manner, then what, according to the conservation of energy, what we can write, this whatever the heat is coming from the heat source, this is generally dissipating over the surface of the plate to it is also conducting to the plate. So, according to I have already discussed this thing in double ellipsoidal model itself. So, according to conservation of energy, what we can write? We can write this Q is equal to which is distributed over the surface of the heat source, which can be represented as like minus infinity to infinity e to the power minus a x square dx into integration of minus infinity to infinity e to the power minus b y square dx, okay, and here q m is there. Always you should keep it in mind, this is heat flux, not heat per unit volume, its unit is, always you should keep it in mind, it is generally here as it is integrating this q m unit is watt, always you should keep it in mind, its q m unit is watt per meter square, whereas q unit is watt, this you should keep it in mind. So, according to conservation of energy, this equation we know. So, I have already discussed this thing in details, generally this you can write as q m into 2 into integration of 0 to infinity e to the power minus a x square dx into 2 into 0 to infinity e to the power minus b y square dy, it should be dy. Okay. So, we know these things already I have derived in my previous Goldak equation. So, we can write these things as directly I am going in next slide.